you. Well, good morning, everybody. Glad to see you back again. Just a couple of housekeeping notes in case you didn't hear. The first two lectures are now on the OLLI YouTube site. Barry has the slide decks for the first three lectures now in both Keynote for Apple or PowerPoint for Windows. And especially when we get to the math part, sometimes it's nice to go through the slide deck. If you really get into the math or you want to understand it or review it, it's kind of nice to go through the slide deck because you can just go at your own pace. And you might remember one of the themes I mentioned is in the first lecture at the very beginning, there were a couple of themes. And one of them was the synergy between advances in mathematics and advances in science. And you see that throughout the history. We started with a lot of geometry with the ancient Greeks. And even during the scientific revolution, we will see Newton still relies a lot on geometry and trigonometry. Symbolic algebra, I guess, was just starting to come into play. We're going to do a fair amount of symbolic algebra at the end today, and hopefully everybody gets comfortable with that. Try to keep it, step by step, so everybody can follow. But again, without understanding the development of the math, I don't think you really have an appreciation of how science progressed. So that's why I've made the attempt to really bring in enough mathematics so you can see how their thought processes were developing.
Yep, I set that microphone up there. You want to just hand that to me?
Yeah, I wonder.
Get it out of there.
Okay. That's not serving any purpose. Okay. So anyway, that's the background. So today, you might remember from last week, I have this slide of the timeline, the stars of our show. We talked about Copernicus and Galileo last time. And today we're going to start talking about Brahe and Kepler. They make a nice pair. They really go together, as you'll see, if you don't already know their relationship. I'm going to sometimes refer to him as Tycho because that's easier for me to say. Tycho Brahe was the Danish astronomer, and Kepler, of course, was the German astronomer in our story. So let's go ahead and get started. And then we will get to Newton a little bit because today I want to at the end I want to introduce Newton's laws, and that'll give us the tools we need for next week. And next week will be the last lecture. So Tycho, he had a real passion for gazing at the night sky. He was doing this almost every night, as far as I can tell, for his career, 30 or 40 years. And he was using instruments called sextants and quadrants. This is just before the telescope. Remember, Galileo's going to not invent the telescope, but improve it enough to be useful for astronomy. But that's going to be just a few years after Tycho's death. So he's using sextants and quadrants, and they allow him to measure with pretty increasing accuracy the angles between the planets and the fixed stars. Remember, they were now able to use the fixed stars as kind of their coordinate system, their roadmap, and then they could see how the planets were moving relative to the fixed stars. He was a meticulous recorder of data. He kept notebooks. This is a page from one of his notebooks in 1577. He was tracking the movement of the Great Comet of 1577. I think you can see he's making drawings to track its movement over the nights. And he was continually trying to improve his instruments, and a quadrant or a sextant is limited by its size. But the bigger you make it, the more accurate it is, which kind of makes sense. So apparently at one point he built one that pretty much filled a large room. And again, I'm going to use my assistant narrator here at times. Let's check the sound, make sure it's loud enough. Whoops. Oh, I wonder if the sound isn't going through to the speakers.
Did we test the sound?
I don't think we did. Yeah, that's probably it.
Right.
Okay.
Yeah.
By King Frederick II
There
of
we go.
Denmark. As
Okay,
part of that arrangement, Tycho said,
thank you. Go back and start that slide from the beginning.
for most of his career, Brahe was supported financially by King Frederick II of Denmark. As part of that arrangement, Tycho served as royal astrologer. The job entailed compiling an annual almanac that predicted the fortunes of the kingdom for the year, based on the influence of the stars. As a matter of fact, throughout the Middle Ages and the Renaissance, astrology was typically taught at universities as part of the astronomy curriculum. For many astronomers, the practice of astrology helped pay the bills.
Yeah, it's interesting. From my reading, you kind of get the sense that Kepler and Tycho were doing these astrological predictions. Sometimes they would do it for a newborn child to talk about the fate of the child or to predict what the events of the coming year. Sometimes they were personalized, sometimes they were for the entire kingdom. And you get the sense that being good scientists, they weren't quite sure they really believed in it, but it was lucrative enough. It was probably hard to give up because that's what the kings and the wealthy people wanted. They wanted the astrology part. Some of them were interested in the science too, but anyway, kind of interesting. So Tycho was not entirely happy with either Ptolemy's model or the Copernican model. So he came up with a third model, kind of a hybrid between the two. So in Tycho's model, he had the Earth at the center of the solar system or universe. It doesn't move. The moon and the sun go around the Earth, but the other planets go around the sun. So he liked that. We all laugh because, now we're getting so complicated, but believe it or not, all three had certain things they were better at in terms of predictions. So there was intense debate going on about these three different systems. In fact, some astronomers tried to improve on Tycho's model. So the final answer was still up in the air at this point. I want to show you a short animated video, a biography of Tycho's life. I think you'll enjoy it. It covers, it does a really good job of covering, giving you a flavor for Tycho's life and career in only 4 or 5 minutes. I didn't think I could improve upon it, so I'm just going to show it to you. It was written by a middle school science teacher from Minnesota, and it was produced by TED-Ed, which is a spin-off of TED Talks, TEDx. So let's just go ahead and watch it.
You imagine the life of a scientist, boring and monotonous, spending endless hours in the lab with no social interaction? Maybe for some, but not Tycho Brahe. The 16th century scholar who accurately predicted planetary motion and cataloged hundreds of stars before the telescope had been invented also had a cosmic-sized personal life. Tycho Brahe was born in 1546 to Danish nobles, but at age 2 was kidnapped to be raised by his uncle instead. His parents didn't seem to mind. Tycho was supposed to have a career in law, but after witnessing a solar eclipse at 13, he began spending more time with mathematics and science professors who taught him the art of celestial observation. By the time Tycho's uncle sent him off to Germany a few years later, he had lost interest in his law studies, instead reading astronomy books, improving his instruments, and taking careful notes of the night skies. It wasn't long before his own measurements were more accurate than those in his books. While in Germany, Tycho got into a bit of an argument with another student at a party over a mathematical formula, resulting in a sword duel and Tycho losing a good-sized chunk of his nose. After that, he was said to have worn a realistic prosthetic of gold and silver that he would glue onto his face. Fortunately, Tycho didn't need his nose to continue his astronomical work. He kept studying the night sky and creating all sorts of instruments, including a building-sized quadrant for measuring the angles of stars. After months of careful observation, Tycho discovered a new star in the constellation Cassiopeia. The publication of this discovery granted him rock star status and offers of scientific positions all over Europe. Wanting to keep him at home, the King of Denmark offered to give Tycho his own personal island with a state-of-the-art observatory. Called Uraniborg and costing about 1% of Denmark's entire budget, this observatory was more of a castle, containing formal gardens, rooms for family, staff, and visiting royalty, and an underground section just for all the giant instruments. Tycho also built a paper mill and printing press for publishing his papers, and a lab for studying alchemy. And since no castle would be complete without entertainment, Tycho employed a clairvoyant dwarf named Jep as court jester. Tycho lived on his island, studying and partying for about 20 years. But after falling out with the new Danish king, he took up an invitation from the Holy Roman Emperor to become the official imperial astronomer in Prague. There he met another famous astronomer, Johannes Kepler, who became his assistant. While Kepler's work interested him, Tycho was protective of his data, and the two often got into heated arguments. In 1601, Tycho attended a formal banquet where he drank quite a lot, but was too polite to leave the table to relieve himself, deciding to tough it out instead. This proved to be a bad idea, as he quickly developed a bladder infection and died a few days later. But over 400 years after his death, Tycho still had a few surprises up his sleeve. When his body was exhumed and studied in 2010, the legendary gold and silver nose was nowhere to be found, with chemical traces suggesting that he wore a more casual brass nose instead. Tycho's mustache hair was also found to contain unusually high levels of toxic mercury. Was it from a medicine used to treat his bladder infection, a residue from his alchemy experiments? Or did his quarrelsome co-worker Johannes Kepler poison him to acquire? We may never know. But the next time you think scientists lead boring lives, dig a little deeper. A fascinating story may be just beyond the tip of your nose.
So that's kind of fun. Just a couple of footnotes, because these stories, you just can't make them up, right? The source I read didn't say that the uncle kidnapped him as a child. It just pointed out that Tycho was born to parents who were wealthy, but they had 7 or 8 other children. And Tycho was probably the brightest. So maybe he went to the uncle because the uncle could afford to pay for his education, and the uncle wanted to get him into law. Of course, he didn't like that. Or maybe the parents were happy to get rid of him because he was kind of a nuisance or a problem child. Anyway, there's that. You also might have heard that he, excuse me, he eventually wound up putting his quadrants and sextants and instruments in an underground laboratory. Obviously, it had to have a roof that opened enough to let the starlight in, and so on and so forth. What I read was he found that when he had the instruments above ground, even if they were inside a building, it was subject to tiny movement, maybe the wind or whatever. He found he got better results by putting them underground, and there was less movement. And so that's the extent to which he goes to get really precise measurements. Another footnote was, I think you heard the part where his patron, King Frederick II, dies. By that time, Tycho, perhaps because of his personality, had already made enemies with a couple of the advisors on the king's court. And the heir to the throne was only 11. So you can imagine these regents who were pretty much controlling the kingdom and managing the budget decided that Tycho was getting too much money. It wasn't worth the budgetary expense. And by the time the next king came along, well, he wasn't interested in science. So Tycho realized time to get out of Denmark. But it was really kind of fortunate that he wound up getting the patronage of this Holy Roman Emperor. And we're going to get to that. And so the story goes that Brahe, Tycho, and Kepler are going to wind up in Prague together, which is really a fortuitous set of events. And so let's tell that story.
Rudolf II was the Holy Roman Emperor who brought Brahe to Prague. Rudolf was a member of the Habsburg dynasty. He had close ties to what was then Bohemia, and he moved the Habsburg capital from Vienna to Prague, with the clear ambition to make Prague one of the top cultural centers of the late Renaissance. He was a patron of the arts and attracted many of the best contemporary painters to Prague. He was also a patron of the sciences, with a special interest in astronomy, astrology, and alchemy. Brahe's widely recognized credentials in those fields made him the obvious choice for the position of official imperial astronomer. But how did Kepler wind up in Prague as well?
Yeah, so that'll be the next question we'll answer with a little story, but I'll just point it out. I'll point out, my wife and I took a trip to Central Europe just in September, and we went to Vienna and Prague. We learned about the Habsburg dynasty. The chin, that you got it. He's got the Habsburg chin. There you go. Apparently the Habsburgs, the way, I think the joke goes something like, you know, some empires are established through war. The Habsburg Empire was established through intermarriage, but they were marrying elites from other countries, but after a while, they were all related to the Habsburg founders. So they were interrelated and they were marrying their cousins and so forth. In fact, there's a show on Netflix now called The Empress. It's about Franz Joseph, the Austrian emperor who was the emperor that's when World War I started. He married his cousin, Elizabeth, she was from Bavaria, but she was a first cousin. So anyway, the Habsburg chin is blamed on this intermarriage, but it was quite distinctive, and it apparently got a little bit worse every generation. Okay, so here's Kepler.
Kepler was a mathematical whiz kid who developed a passion for astronomy at a young age. He studied mathematics and astronomy at the University of Tübingen, where he became a staunch supporter of the Copernican system for both theoretical and theological reasons. Upon graduation, he took a job as a mathematics teacher, but found time to write about his theories on the structure of the solar system. Like Brahe, he developed a side gig as an astrologer, even while doubting its scientific basis. He published a book entitled Mysterium Cosmographicum, which gained him a favorable reputation among European astronomers. He attracted the attention of Tycho Brahe, and they began a correspondence discussing and debating their ideas. Brahe was impressed enough to invite Kepler to work with him in Prague. At that time, Kepler was convinced that God's plan for the universe would be based on the abstract perfection of geometric objects. In his early approach to astronomy, his guiding principles constituted a sort of geometrical mysticism.
Okay, and if you're wondering what I mean by that, let's go and take a look. What was this Mysterium Cosmographicum all about? Okay, so remember that Kepler, like Copernicus, Kepler believed that these orbits were perfect circles. That just made sense. And by this time, he was aware of the relative sizes of these orbits, and he was going to try to understand the ratios between the different orbits. They were perfect circles. Let me show you in a minute what I mean by their ratios. But again, just remember, last time we talked about this, how they were now able to use simple trigonometry to at least gain insight into the relative sizes of these orbits, because they could compare them to the radius of Earth's orbit as they understood it. But they could take any planet, figure out its relative size, and then you could figure out the relative sizes from one to any other one. So what he does, I'm kind of imagining what he does, but it's not any stretch to say this. he looks at different orbital pairs. And so you can see the list here. He's creating a table. And then the ratio that you see on the right is the ratio of the, well, it's actually based on our current understanding. So these were not the numbers he was looking at, but they were probably similar. But this would be the modern understanding of the distance, let's say, the average distance of Venus to the sun compared to the average distance of Mercury from the sun. You get a ratio. And so these are the ratios that we now understand. And again, they're just a stand-in because I don't know exactly what Kepler was working with. They were probably, you know, off by 5%, 10%, I'm not sure. But anyway, he had some ratios in mind, and he notices that they vary over a range, but there's no particular pattern. And he doesn't like that. He doesn't like anything irregular. He thinks there should be a perfect, as they say, geometrical reason for these different ratios. Because he believes in a creator of the universe, and so it wouldn't be haphazard.
Let's imagine what Kepler might have done. He starts to make a table, let's say. So there are 6 known planets and 5 pairs of adjacent orbits. Kepler was interested in the ratio of orbital radii within each pair. No.
So you get the idea. I forgot that I had a recording for that one. So anyway, so he gets interested in regular polygons. As a geometer, those are nice and symmetric. If you remember, a regular polygon is a polygon, has a certain number of sides, but every side is the same length, and all the internal angles, like in a square, they're 90 degrees, they're all equal. That's a regular polygon. They have a certain perfection in Kepler's mind, so he takes a square. Now, draw what's called an inscribed circle, and then draw what's called a circumscribed circle. And then the question is, what's the ratio of the larger to the shorter radius? And then you might choose a different regular polygon. How about an equilateral triangle? And you ask the same question, what's the ratio? And then he's going to go back to his table. He's got a column here for put in a regular polygon, and then another column to document the ratio of the radii of the circumscribed to the inscribed circles. So for the square, that ratio turns out to be 1.41, 1.56 for the equilateral triangle. And he finds a nice spot for both of those. Here's that radius, pretty close to Earth to Venus. And then for Mars to Earth, pretty good match. So he gets interested, but it's a dead end. When he goes on to the next steps, he's not making any progress. The numbers actually get worse as you go on. And so he decides, okay, not going to give up, but he decides to think in terms of 3 dimensions. Well, where am I going with this? Remember that there's an infinite number of regular polygons. You just pick the number of sides and you can create a regular polygon. But in geometry, going back to the ancient Greeks, there's something called the 5 Platonic solids. You might ring a bell. If it doesn't, that's fine. But these are rather, again, almost mystical objects because there's only 5 of them. And they vary, of course, by the number of sides. But after you get up to about 20 sides, there's no more after that. But the defining feature is this. They all have flat surfaces, as you can see, and all the surfaces on a given Platonic solid are identical regular polygons. So we get back to regular polygons again. So, you know, Kepler being the sort of mystical geometer that he is, he gets excited about these. So how does this work? Well, okay, so going back to 2 dimensions for a minute, but again, we're talking about now each orbit defining a sphere, and I'll show you the spheres in a minute, but think of terms of spheres. There's 6 planets, there's 5 gaps. So that's nice, 5 Platonic solids, 5 gaps. And as you'll see, he fits the octahedron here, icosahedron, dodecahedron, tetrahedron, cube. And let's look at the ratios. Well, I'll show you the ratios in a minute, but these are 3D images from one website. Somebody took the trouble to sort of actually draw this out. But I'll just scroll through these. You get the idea. But they're the platonic solids are sort of nested in between the two spheres. It's kind of pretty. It's appealing. So he puts down the platonic solids here. And then he writes in the ratios. And again, remember, he's dealing with different numbers over here. I don't know what they are. And even then, he knows that there's still a degree of uncertainty. See, he doesn't have Tycho's data yet, but he thinks if he gets better data, he might change the radii that he's listed here, the ratios here, and maybe they're going to match up. So he really takes off with this idea. And again, it seems rather silly to us, or doesn't make sense, but it was good enough to write this book, Mysterium Cosmographicum, and it drew the attention of Tycho. And so Tycho starts writing, they write back and forth, and pretty soon Tycho invites him to Prague. So if he hadn't had this crazy idea, he might never have gotten the attention of Tycho, because Tycho was only in Prague for about 1.5 years. He wasn't there very long. So there was a very small window of opportunity for Kepler to actually work with Tycho.
So
Yeah.
to clarify, so the ratio, the column on the right
Yeah,
is the observed ratio radii.
based on modern observations.
Observations.
Right.
Yeah.
And so we don't know what he was working with. Yeah.
But modern, and at the time, they must have known that these change with time, right? Because they're not fixed ratios.
Well, no, that's all. Remember, they thought they were perfect circles.
Right,
And there was also this belief that nothing in the heavens ever changed.
right.
So these, they didn't have the exact numbers. They knew that their data had errors in it, but they believed that there was a fixed ratio that was the actual ratio, and they were trying to get closer and closer and closer to it through their observations.
Right, but the actual observations would show variations, right?
Well, we're going to come to that.
Yeah.
I mean, Kepler is the one who eventually figures out they can't be circles.
Oh, okay.
Yeah, we're going to get to that, but this is still earlier in his career, and he wants to get Tycho's data. So yeah.
Your drawing shows the circle's not precisely concentric. Did they assume it was, they were all equally distant? Or that they're offset? Your diagram showed the offset.
Well, there again, they had to play around. Their data suggested that the center of each orbit was not exactly the sun. They had to fudge it. I think they were hoping that if they got better data, maybe it would be perfect concentric, but they were sort of playing around with that. Yeah.
And just another question, Jeff. So you mentioned a couple of times that they all did astrology, right? So was that a side gig, or was astrology so influential to early astronomers in terms of heavens, observations of the heavens, and the fact that they were looking for some geometric pattern? Did that come from astrology to help do the research?
Well, I think that's a very good question, and I think the answer is somewhat nuanced.
Yeah.
And it might depend on the particular person, but kind of goes back to, remember what we said the first lecture, the ancient Babylonians and Egyptians, for them, astronomy was inseparable from their religion, their mythology. So the two were one and the same. Then the Greeks came along and they wanted to say, let's not explain things with religion or myth. Let's just look at the natural world and not look for supernatural explanations. But then the Middle Ages, I think superstition comes into play again. The people in the Middle Ages, that's why there wasn't very much going on in science in the Middle Ages, because the superstition kind of. So what we see in the Renaissance and the scientific revolution is this tension between superstition and real science. And this is where these people are. And you'd have to be able to get inside each astronomer's mind to know whether they really believed in it or not. Yes.
If I'm remembering correctly, I think there's a astrological prediction by Kepler up in special collections at McHenry on campus.
Interesting.
Yeah.
Yeah, that'd be worth taking.
And I think it was for some king or something.
Uh-huh.
Yeah.
Uh-huh.
I don't know. It's a long time since I thought about it. But
Yeah. Well, and I think you heard a little tone of cynicism when I said there was money to be made through astrology.
Right.
And so maybe it was nice to play along, even if you didn't really believe in it.
I would.
These are wealthy and powerful individuals, wealthy individuals, and they want to know their horoscope. Okay. So anyway, as I say, kind of to us, kind of an outrageous idea. Maybe Kepler is a good scientist. Maybe he doesn't believe in superstitions and astrology, but he does believe in a creator who would create a universe that would make sense somehow. It wouldn't be random. And so that's, again, that's that nuance between a true natural science where you take supernatural things out of it. There's still they still allow for some interplay between a supernatural creator and purely natural explanations. This is just an illustration from the Mysterium Cosmographicum. When you look at it, you would have to scratch your head and say, what's going on with that illustration? But now I think you have some feeling for what he's trying to do there. He's just trying to cram all of those Platonic solids into one drawing, which is hard to do. Okay, so let's carry on with our story.
Now, as the cartoon suggested, the relationship between Brahe and Kepler was turbulent at times, complicated by a combination of mutual respect and mutual resentment. They were very different people. Brahe was born to nobility. Kepler was raised in relative poverty. Brahe was arrogant and self-aggrandizing. Kepler was modest and self-effacing. Brahe was the fanatical empiricist, the meticulous collector of data. Kepler was the idealistic theorist, searching for the grand design that underlay the structure of the universe. But like any good theorist, Kepler knew that his theories were worthless unless there was data to back them up.
Yeah, so one little footnote to this story regarding Kepler's childhood. And again, just to remind you of the times that we have to remember when we talk about these people. Apparently Kepler's mother was an herbalist. She studied herbal medicine, and she was producing remedies through natural medicines and treating people. Well, the authorities got wind of this and decided she was a witch. And she was accused of being a witch and was imprisoned for a period of time. She was not executed, but she was imprisoned. So Kepler had that on top of everything else growing up. So imagine, well, it's hard to imagine, but. So here comes Kepler, and Brahe's got all this data, and Brahe, Tycho maybe doesn't have time to analyze it, or he thinks Kepler's got a good sense of how to handle all this data and make sense of it. So he hands Kepler his first assignment, which is to look at the data for Mars. And this was actually somewhat of a lucky fact, because a lucky event, because as you might know, the planetary orbits aren't too far from a circle. They actually, I mean, they are elliptical, but they're not that elliptical. But Mars is the most eccentric. And so when Kepler looked at this data, it was, of all the data he might have looked at, it was going to be the hardest one to try to make it into a circle, to reconcile it with this idea of the circle. So long story short, at this point, and now Kepler's still relatively young, but he's had these ideas of the Mysterium and this perfect series. He now has to face the fact they're not circles. So what's going on with Mars?
The data pointed to an undeniable and monumental truth. The orbit of Mars was not a circle. Meanwhile, when Brahe died, Kepler naturally expected to take possession of all of Brahe's data. However, Brahe's heirs had other ideas. They viewed those records as valuable assets belonging to Tycho's estate and tried to establish sole right to them. Fortunately for the progress of science, Kepler eventually won that battle although possibly by illegitimate means.
Kepler was not going to let the family hold on to that data. There's no way. Let's see. Oh, yes. So Kepler has to abandon the idea of a circle or a sphere, and he comes up with the idea, maybe it's egg-shaped, maybe it's an ovoid. All right, well, it has a certain symmetry to it. I suppose if it's an ovoid, the sun would be the yolk.
Right.
That's an astronomy joke. Not a very good one, but that's, or you could say it's an astronomy yolk. It gets worse. Because in the end, the joke or the yoke was on Kepler. I'm sorry. The joke is on Kepler in the following sense. After struggling with ovoids and other things, he finally realizes it's an ellipse. And then he goes, how did I not think of that sooner? Well, why haven't other people thought of it? Because remember, a circle is actually a specific kind of ellipse. It's a special ellipse. So the ellipse is not that big of a jump from a circle, but it took a while to get there. So let's just remind ourselves of some of the features of an ellipse. You might remember this from geometry, but first of all, it has two foci, one there and one here in this case. And he wanted to put the sun at one focus, which was a good idea. And the defining feature is this. If you pick a point on the circumference of an ellipse, any point you want, and you draw a line from, let's say, that point there to here, and from that point to the other focus, D1 and D2, if you add those together, it's a constant for any given ellipse. So no matter which point on the circumference you pick, that sum, after you draw it out, will always be a constant. That's how you define an ellipse. The other feature is the major axis, which is the longer axis going through the foci and the center. It represents the longest dimension of the ellipse, and then the minor axis represents the shortest dimension of the ellipse going through the center. A couple other little notes. It's sometimes convenient to talk about the semi-major axis, which is simply half of it. So from the center to one vertex, the semi-major axis. And oh, the other thing is the eccentricity of the ellipse. That's just a measure of how flattened it is. So if it's almost a perfect circle, that's low eccentricity. This one would have sort of more moderate eccentricity because it's so elongated. So we'll come back to ellipses, trust me. Now, Kepler also knows the following. In fact, he discovered this law first. It's his second law, but he discovered this one earlier. And that's the fact that he knows from Tycho's data that when the planet is closer to the sun, it moves faster. And then when it's farther away from the sun, it moves more slowly. And so he wants to understand that relationship, and he finally hits upon the answer. You might remember this. Planets sweep out equal areas at equal times. So over here, where the planet is close to the sun, it's moving faster, it covers a greater distance compared to over here when it's farther away from the sun. But interestingly, when you measure the area, that wedge, this wedge and this wedge are the same in terms of their area. And that's a fact. So he figured that out. And we'll come back to that. And then his third law is his successful attempt to relate the period of the orbit. The period of the orbit is simply one cycle. The planet starts here. The period is the time it takes to get back to that same point. And remember the semi-major axis, A. So the square of the period is proportional to the cube of the semi-major axis. That's Kepler's third law. So here they are, the three laws, the law of the ellipse, equal areas swept out during equal times, and then the formula for the orbital period in terms of the semi-major axis. But here's a little summary.
Kepler's 3 laws are all correct, but he arrived at them by trial and error. They describe patterns within the data, but he still has not found an underlying set of fundamental laws that would account for those patterns. That undertaking became known as solving the Kepler problem, and that's exactly what Newton is going to do.
Solving the Kepler problem. Before we leave Kepler, just want to leave you with a couple of comments. Kepler had a notion of gravity, and let me share that with you. This is something he wrote.
Gravity is a mutual corporeal disposition among kindred bodies to unite or join together. If 2 stones were set near one another in some place in the world outside the sphere of influence of a third kindred body, these stones would come together in an intermediate place, each approaching the other by a space proportional to the mass of the other.
So interesting. He's thinking about a mutual attraction based on the mass of these 2 objects. Very good.
The theory of it actually,
He had a theory. Yeah, he had a theory of gravity.
right?
And one last comment from a contemporary mathematician, thinking of Kepler as the virtuous scientist.
Well, Kepler was one of the most open and unabashed of mathematical writers. He never hesitated to describe blunders, wrong turns, or dead ends alongside his true discoveries.
That's what you need if you want to be a good scientist. You have to be able to give up your ideas when they prove to be wrong. That's another theme. But again, apparently he did acknowledge his mistakes in writing, so he was willing to be accountable for them. Like I say, when he discovered that it wasn't an ovoid, it was an ellipse, he said, "Oh, what an idiot." Of course. And that's going to bring us to Newton. So let me go forward here. As I said, we want to cover Newton's laws today, so we're prepared for next week. We'll just go through them. He had 3 laws of motion. The first was the law of inertia. A body moving with a constant velocity, including a velocity of 0, will continue with that same velocity unless a force acts upon it. That's the law of inertia. That comes from Galileo. You got to give Galileo credit. And others perhaps, but we know Galileo thought of in terms of inertia. And then number 2, force equals mass times acceleration, F equals ma. That gets drilled into your head if you take physics. So let's think about that. Let's play around with this idea of force equals mass times acceleration. So let me show you this little video. Again, there's going to be a force from the motorboat, and the child is going to be accelerated. He's not going to be moving with a constant velocity. It's a constant force, but the acceleration leads to an increasing velocity. And just to give you a visual image. Nothing surprising there, but I'm just making the point. Think of the force having a source. There has to be a source for the force, and the force is the cause of a movement. Acceleration is the result of the force. So cause and effect. And if the force is constant, the acceleration will be constant. And then the mass, in this setting, the mass is kind of a measure of resistance to movement. So you can think of it that way, which means if the mass is larger, the acceleration is going to have to be lower. So the adult is going to be accelerating at a slower rate. Okay, that's all pretty self-evident. Now, we're building to the 3rd law. It's said that actually Robert Hooke, who was a contemporary of Newton, had an idea about gravity also. And he postulated that any two heavenly bodies will have a mutual or reciprocal attraction to each other. And so again, you know, Newton didn't come up with these ideas on his own. There was a history to these ideas. The problem was to prove that they're correct. But anyway, this brings us to the third law of motion. For every force, there is an equal, opposite, and reciprocal force. For some reason, I think most of us are taught, I know I was taught that it's worded for every action, there's an equal and opposite reaction. The problem with that is nobody ever defined what an action is. It apparently does have a definition, but I think it's just clearer to say for every force, there's an equal, opposite, and reciprocal force. And that applies to gravity, but it applies to any situation. For example, with the motorboat and the water skier, the boat is pulling the water skier, but at the same time, there's a force based on the water skier resisting that motion and creating a force on the motorboat. And then again, we talked about Kepler. This is just a summary of
Gravity
Kepler.
is a mutual corporeal disposition among kindred bodies to unite or join together, each approaching the other by a space proportional to the mass of the other.
So with this in mind, with these ideas in the air, so to speak, we might imagine Newton beginning to come up with a law of gravitation, and he's going to make it a universal law of gravitation. And that's important. It applies to the heavenly bodies, but it also applies to gravity on Earth. So we could say that the force of gravity is proportional. Give us just the proportionality symbol, some constant. But the two main factors are the mass of the sun and the mass of the planet. In this case, got to multiply them together. Or we go back to Galileo and the Leaning Tower of Pisa, we would say the force of gravity is proportional to the same constant, because it's a universal constant, times the mass of the Earth times the mass of the ball. And so what I'm showing here, the two balls are the same size. So to be rigorous, they have the same air resistance, but the solid ball is obviously heavier than the hollow ball, but they fall at the same rate. So again, the reason that they fall at the same rate, we can now understand it because we've got these laws. On the one hand, the solid ball is heavier, has more mass. So gravity, the gravitational force is going to be greater on the solid ball, but mass is also a resistance to acceleration. And they counterbalance each other. So it doesn't matter, as long as they have the same air resistance, or if you do it in a vacuum, we talked about that, you can drop a feather in the vacuum and it'll fall just as fast as anything else. They fall at the same rate, so acceleration is constant. There we go, force of gravity. In this case, gravity being the cause and acceleration being the result. So the crucial next step is to make this an inverse square law. And it's, according to one source, there were several people around the time of Newton or before Newton, shortly before Newton, who were thinking in terms of an inverse square law. We're going to look at that after our break. But this was a crucial step. And it was out there in circulation as an idea. Some people came up with it for different reasons. But we're going to look at that a little bit more carefully right after the break. So, intermission. Why don't we take maybe 5 minutes or so? So as I say, this inverse square law is a very important step. Not sure exactly how Newton, I haven't read enough, let's say. I haven't read his Principia from cover to cover.
Well,
I've had to sort of cheat. But anyway, it was a very important step. But again, it was the idea was in the air, so to speak. But how do we? There is a logic to it, and maybe this is familiar to you. But let's just go through the logic of why it should be an inverse square law. And to do that, we introduce this concept of a gravitational field. So instead of a gravitational force, we're going to call this a field. We'll see, it's a little bit different. I'm going to use the cursive F. And the difference is, as you see, there's just one body here, the sun. we've taken out any other second body, planet or other one. And we're just thinking in terms of an abstract concept of a field. And we have field lines, and these field lines all point towards the sun. That's the center of the gravitational field. And again, this is 2 dimensions, but think in terms of 3 dimensions. Now, again, these lines do not exist in real life, but we draw them in, and that's allowed as long as, if we're going to really get serious about it, we have to draw the right number of lines based on how strong the gravitational field is. But let's just say that we've taken that into account. So I've drawn a certain number of lines here. And so the field, the gravitational field, is proportional to the number of lines that I've drawn. But remember that the number of lines is really just a stand-in for the mass of the sun. So if the mass of the star was bigger, you'd have to draw in more field lines. That's all. But now what you can do with this concept is you can say, okay, now again, thinking in 3 dimensions, imagine a sphere with the sun at the center of the sphere. If there is a planet anywhere on this sphere, because it's all symmetric, it's going to feel a certain force now, because we brought in the mass of the planet. And no matter where it is on the sphere, it'll feel the same force, it'll experience the same field, because it's equidistant from the sun. To be more precise, again, and let me let our narrator tell the rest of the story.
In this model, a planet located anywhere on the surface of the green sphere will be in the gravitational field. The strength of that field will be the same everywhere on that surface. And yes, the strength of that field will be proportional to the number of field lines, but more precisely, its strength will be proportional to the density of those lines running through the sphere's surface.
In other words, the surface area is important. So the gravitational field is directly proportional to the number of field lines or to the mass of the sun, but it's inversely proportional to the surface area. So that if you have a bigger sphere, it's the same number of lines, but it's a bigger surface area. So now the gravitational field, the strength at any point on the larger sphere is going to be smaller. That's the leap. And of course, the surface area is proportional to the square of the radius, again from geometry. And so now we can rewrite gravitational field like that, or we can go like this, put the mass of the sun in. And if we get tired of this proportionality sign, let's actually put a constant in. I was calling the constant K earlier, but ta-da, there you go, Newton's gravitational constant. So this is a true statement of a gravitational field. And we only have to do one little adjustment to get all the way back and complete the circle to the force of gravity. We put gravitational field times the mass of the planet. So the field is very closely related to the force of gravity, but it's just you take away the planet so that it's not specific to the planet per se. And so there's Newton's universal law of gravitation. Any questions so far? Is this easy enough to follow? So there we are. We can summarize the laws that are going to be important that would allow Newton to solve the Kepler problem. And as we go forward, just remember the concept of the field is very closely related to the concept of the gravitational force. So now we're going to play around some more with his second law. Yes?
The gravitational constant, tell me more about it. What is it?
Oh, okay.
Where did it come from? Is it like out of thin air? Or?
Well, it's partly to resolve differences in units. So if you talk about mass and acceleration, mass times acceleration means you've got, let's say, kilograms times meters per second per second. Force Well, it requires a unit of its own. It's such a fundamental concept, and the unit that people came up with was newtons. All right. But again, probably because the sun is so huge, it's a way of adjusting the right side of the equation with the left side of the equation is all, so that you're working with numbers that are manageable. That's all. And yeah. If you change the gravitational constant, well, then the measure of force would just have a different number to it. But by this time they were already using pounds maybe as a measure of force, so it was some way to equate pounds or megapounds with kilogram times velocity times speed times distance divided by second. So it's just a way of working out the units and the dimensions. With Galileo and his experiments on the ramp with the rolling ball, we talked about this. You might remember acceleration by definition is really just change in velocity divided by change in time, which is true as long as the acceleration is constant, which is true as long as the force is constant. But on those inclined planes, the acceleration was constant because the slope of the ramp didn't change. So this is true. So we can write it this way. Now let's do here's a little trick. We're going to multiply both sides of the equation by delta t, which is the time lapse. That's simple enough, but look what it does. We're dividing by delta t and then multiplying by delta t, so those drop out. And this might not look that much simpler, but now we're going to define a new term. It's called impulse, I, and that's a real term in physics, and it's equal to force times delta t. In order for a force to have an effect, it has to operate for some discrete period of time. That could be indefinite or it could be very short. Whatever that delta t is, that defines the impulse along with the force. So here's a visual image of an impulse. We have any Dodger fans? A baseball bat and the ball. So to our eye, the ball is in contact with the bat for an imperceptible duration, but it isn't zero. It's there for a certain fraction of a second, and that it requires that definite time period to transfer the force onto the ball. And if you look at it in time lapse, the ball actually compresses quite a bit. You may be aware of that. Yeah. And the bat vibrates. That's why the bat can break. So impulse. The point is, delta t can be very small, but if the force is great, it can have a big effect. And we're going to get to that. So that's impulse. So now we can say impulse equals mass times delta v. We could stop there, but just to make it even simpler, I'm going to divide both sides by m so we can get rid of the m, the mass. And so now impulse divided by mass equals delta v, and I'm going to call this the specific impulse. I just want to make this as simple as possible. It really wouldn't matter, but the point is, if you have a force applied for even a fraction of a second, that's an impulse, and the net result is simply a change in velocity. It could be in the same direction of the velocity that something's already going, or it could change the magnitude and the direction. But delta v is itself a velocity vector. So impulse, in this case, the force, of course, we're talking about is gravity, but let's just make that clear. And gravity, of course, that's Newton's law. But if we divide both sides by m, little m, we get the specific impulse is basically the gravitational field times delta t. So there's the gravitational field, and that's going to equal delta velocity. Any questions? That kind of makes sense. Again, this is symbolic algebra. It's just manipulating variables or manipulating symbols and defining new terms. But it's really airtight as an argument. It's pure deductive reasoning. That's what this is, as you manipulate equations. And that's why, you know, Newton gets credit for being the person who used deduction to prove, well, to solve the Kepler problem, as we'll see. So from now on, if I say impulse, I'm referring to this thing I've called specific impulse. It really wouldn't matter, but again, just think impulse means field of gravity is turned on for a split second, because we're going to do that. We're going to turn gravity on and off. That's just kind of a heads up. It's a thought experiment.
Mhm.
Would be neat if we could do it in real life, wouldn't it? But you can't. You can't turn gravity off. But if you could, it would lead to some interesting ideas, as we'll see. So a gravitational field times delta t is going to produce a change in velocity. So let me just, in wrapping up, again, just laying the groundwork for next week's class. This is a thought experiment. We talked about thought experiments and how useful they can be. So here's the sun. Here's some planet, call it planet Q or planet Earth or Mars, whatever you want, but some planet out here at point A in space at, let's say, noon on a given day. And gravity is turned off. I'm going to give this planet an initial velocity vector, purely arbitrary. It just has for whatever reason, it has this velocity. And since there's no force acting on the planet, it would continue indefinitely at that same speed and direction. But let's stop it 1 hour later, 1 p.m. It arrives at point B. And now I'm also drawing in what we call a displacement vector, which just shows the change in position. But I've scaled the two vectors so that the velocity vector is scaled so that it equals the displacement vector. That's just to make your thinking simpler and more visual. But again, a blue vector is a velocity vector, an orange vector is a displacement vector. But with a blue vector, the blue vector is scaled to show you the distance it would go in 1 hour. That's the point. So 1 hour, it goes this far, which gives us the displacement vector. And so now we're at 1 p.m. at a brief instant in time. The planet is now here and it still has the same velocity vector. So now I've drawn it here and it shows you where the planet would go 1 hour later. But now we're going to turn that gravitational field on for a brief instant, which means brief. I don't know how long, but let's just pick a number, some fraction of a second. But we can also dial up that field as strong as we want. We can play around, but it's turned on for a brief instant. And that's going to create an impulse and a delta V, and we can draw that in. Which way does the delta V point? Well, it points towards the sun, of course. And again, it's the same scale because we're a thought experiment. We can give it any length we want, but I've just given it some arbitrary length. The point is this: now we have two velocity vectors, and we can add those. Remember, we did that before. Just so you don't forget our legend. But a red and a blue arrow are both velocity vectors, so we can add them together. And how do we do that? We move the tail of the red vector up to the tip of the blue vector, and then we can draw the resultant. And so that's what turning the gravitational field on for a brief instant does. It changes the magnitude. This is the resultant. So now the planet has this velocity, which means a speed in a direction. And that tells you everything you need to know. So now, after 1 hour, it's going to be at point C with that given velocity vector. So I don't know, maybe that seems strange to be talking this way. In the end, I think it'll make sense, but if you're following it so far, then you're in great shape, because next week we're going to build on this and solve the Kepler problem. I know you've all been wondering about that Kepler problem. Yeah, full disclosure, it has been solved, but we're going to do it all over from scratch.
Oh, my.
Any questions?
Do you think the elliptical orbits are, you said circles is an ellipse, of
A
course.
circle is a
Is it
special
general
case of an
special
ellipse,
ellipse?
yes.
Are they due to the initial conditions, the initial, how the solar system came about? And it could have been, a planet could actually be circular if its initial conditions have been different.
Yes.
Yeah, okay.
We're gonna
They
get,
don't naturally have to be devolve into an ellipse. They would say circular if they started that way, you think. Okay.
what would happen is, the point is that a circular orbit is possible if you set the initial conditions just right.
Yeah.
But it's sort of like trying to balance a pencil on its tip. It's very unstable. And so if a little asteroid hits the planet, it's gonna knock it out of that circle.
So it would probably devolve into.
Eventually, you're gonna wind up mostly with ellipses because it has to be pretty pristine to get a circle, yeah.
In the big gap between Jupiter and Mars, do people start thinking that maybe there had been a planet there?
Well, isn't that where the asteroid
That's where the
fell?
asteroid
Yes,
fell. So there's some clues that there was a
Yeah.
planet there perhaps.
yeah.
Yeah.
Right, I don't know when that sort of dawned on people, but yeah.
It kind of stands out in those gaps.
Right,
Yeah.
there is matter out there.
Yeah,
It's
yeah,
just,
yeah.
it was maybe a couple of planets that collided or. Okay, yeah, question.
Figure out that the moon doesn't go around the center of the moon.
I don't know.
In a similar way, something disturbed them.
Well, there's two ways to answer that question. Number one, the moon's orbit may be somewhat elliptical. But to be precise, in this case, the moon and the earth, the moon doesn't revolve around the earth. They both revolve around their center of mass. And that's because the mass of the moon is not so different from the mass of the earth. But in truth, and that's how they find, that's one way that they found distant planets in other solar systems. You can detect a wobble in the star. So our sun is wobbling a little bit because all of these planets are orbiting around it. There's nothing keeping it in place. It's being pulled, but because it's so huge, it resists that movement. So for practical purposes, we think of the sun as a fixed object, but it does wobble, just like the earth wobbles a little bit. And also the moon's orbit around the earth is, I'm sure, not a perfect circle. Yeah. Yeah.
One, I mean, this is a pretty naive question, but, where was Newton when he did this great laws?
Oh, that's not,
Was he with the university? Was he under a king's tutelage, or what was going on?
well, that's a very good question. And I haven't looked at his biography in a while. I was going to try and do that for next week, but
Oh, okay.
no, that's good. Still a good question. I mean, it's important to sort of have an idea in your mind where they're doing this. I agree. I think, he was at the University of Cambridge.
Oh, okay.
He had a chair in the Department of Mathematics. So he had a reputation. By the time he was doing this, he was already well known.
Okay.
In fact, next time, if we have time, we'll talk a little bit about the personal side of this whole story. But the three key players are Newton, Halley, and Robert Hooke. Yeah, there was a little bit of rivalry between Hooke and Newton, but they all three were well renowned scientists by that time. And the story, as I recall, is they're sitting in a pub in London, and Hooke says something like, yeah, I've solved the Kepler problem, it's an ellipse, or maybe he doesn't say it's an ellipse, he says, I've solved the Kepler. And Halley looks at Newton, and Newton looks at Halley. Newton doesn't say anything, but then later Halley goes to visit Newton at Cambridge. And Newton says, yeah, I've solved the problem too. And Halley says, well, let me see your notes. And Newton says, oh, they were here just the other day. Let me see if I can find them. So I don't, who knows what was really going on, but Newton was working on the problem. They were all working on this problem, a lot of interest in solving the Kepler problem. It was a big project, and it was probably a contest to see who could come up with the answer first. But Newton was at Cambridge by this time.
Thank you.
Yeah, and Halley, of course, is the guy that discovered Halley's comet. Yes. Any other questions? Well, thank you. We'll be back next week. Yeah.
I want to say that there are